Okay, so we should be going again. Yep, going again. Got an example problem here. Pretty straightforward, simple example here. Let's look at this guy. We've got a rigid, well-insulated vessel containing 2 kilograms of a saturated water mixture with an initial quality of 0.25. So 25% in the vapor phase, 75% in the liquid phase. Pressure of 100 kilopascals. An electric heater is turned on inside the tank until all of the water vaporizes. Determine A, the amount of energy put into the system by the electronic device, the electronic heater, and B, the entropy generated for this process. Okay, well, what is a good way to find part A? It says we want to know the amount of energy, page 3, page 4 is going to be an example. We want to know the amount of energy required to vaporize all this water. So, example. Well, let's collect our givens while we think about what tool we're going to use to figure out that unknown energy. Hopefully that's pretty easy at this point. I've got a rigid, well-insulated vessel containing 2 kilograms. I've got water, quality, and I've got it's changing, so it's going to be the initial quality of 0.25. It's 25% in the vapor phase, and an initial pressure of 100 kilopascals. An electric heater is turned on inside the tank until all of the water vaporizes. So they've told me something there. They've told me X2, the quality at state 2, is 1. Right at the point where 100% reaches the vapor phase, what is the minimum amount of energy required to achieve that? And then what is the entropy generated? And so I've got this tank. I've got some kind of device in here putting electrical work in. We're going to call it a work term because electricity is always work. It converts into heat inside, but when it crosses the boundary, it's coming in as electricity. So we call it work going in. They want us to find A, what is that work, and B, what is the entropy generated. Okay, now there's a couple of other things given here that I've not written down. Maybe you've figured them out already. What do you think they are? Pause it if you're not sure. There's 2 more things that are given here. They're not actually numbers. What are they? Go ahead and pause. Okay, you got them? Well, it's rigid. So the volume is constant. And they told me it's well insulated, so there's no external heat. The only energy crossing the boundary is this work. Now, I asked earlier, what tool are we going to use to find this work term, this energy term? The gag reflex at this point should be, that's a first law equation. So, first law says add the in, subtract the outs, and again, this is an insulated tank, so if you like, draw some kind of insulation on there. All right, my awesome drawing skills there. So the only thing crossing the boundary is this electrical energy coming in, so that's going to be the entire left-hand side. It's a closed system, so in minus out equals change. The only thing changing here is the internal energy. Okay, I know the mass, and I think I can find U's, right? I know I can find U1. I've got P1 and X1. I know I get U1. That's easy. U2 might take a little more effort. All right, we can figure that out though. So how are we going to figure out the entropy generated? Entropy generated. Well, pause if you need a second. Right, so how are we going to find the entropy generated? Well, we just talked about this cool, brand new fancy tool. We said the entropy change, because this is a process going from state 1 to state 2. The entropy change, according to the second law, is the amount of heat transfer divided by temperature added up from state 1 to 2, plus the amount of entropy generated. Well, here's what we're looking for. All right. Now this delta big S here is just going to be m times little s2 minus little s1. I would suggest if I can find u's, I can find these s's. I already know the mass. What do I know about the heat transfer here? If I add up, an integral just represents a summation of a bunch of little tiny things. If I add up a whole bunch of little tiny zeros, I still get 0. So the second law says if I take m times delta S, that equals the entropy big S generator, the entropy generator. Right? Okay. If you're in my class, this is a 25-point test problem. This is probably 7 points. This is probably 8 points. You're at 15 out of 25 right there. You've shown me you know how to get to a solution. Show me how you're going to get to these unknown values, get as many equations as you have unknown. Engineering work's done. Okay? So a lot of the engineering work's already done here. We've identified the major concepts, and we've tried to simplify them to what makes sense for our problem. That's your real goal here. Okay? So let's talk about how do we get to these unknowns. I'm looking for this guy, I'm looking for this guy. That means I need these properties. All right, well, let's go look up properties, shall we? So what do we know about state 1? Well, I know P1, 100 kilopascals, it's water, and I know the initial quality is 0.25. So with that, what do we need here? I'm going to need, for sure I'm going to need U1, and I'm going to need S1. Okay? All right, let's talk about state 2. What do I know about state 2? Well, I know it's saturated vapor. What else do I know about state 2? Pause here if you need a minute. Okay? What do you know about state 2? I need one more property here. I can't just use saturated vapor. I need one more property. The common thing is there anything constant? Not pressure. Nothing says the pressure is constant. In fact, closed system, that's not a good gamble. What else is constant? Volume. So if total volume is the same and mass is the same, that ratio of total volume to mass, the specific volume is the same. So if I can get these properties, I can also get the specific volume in state 1. These two properties will be enough to get me properties at state 2. Now this is a saturated mixture here, so I'm going to have to use quality. So this is going to be, I'm going to have to take my quality times UFG plus UF. Alright, this is going to be X1 SFG plus SF. I don't think, I know in our text we don't have a VFG. I'm going to have to actually compute the difference between VF and VG plus VF. Right? And then state 2, you can go look that one up here. Okay? Well, I've got these numbers here. I'm going to assume that you can do these computations. You can go look up these values. You've got the quality value. I'm going to assume you can do these calculations on your own. Pause it here and go do these and see if you get the same number. So pause it right now. Run these through your calculator. Look these properties up. If you can't do this, you can't do it on test. So pause it now. Go do this. And then I'll give you the answers here. Okay? So this is what I have written down. I'm looking at projection over here, and I'm seeing that U1 is about 939.45. You might get, this might be an older edition of the text that I'm pulling this out of, so you might actually get slightly different, but should be really close to that, within probably 3 significant figures. I'm getting S1 to be 2.8168. That should be kilojoules per kilogram Kelvin. So U is energy per mass, S is going to be energy per mass per temperature. And I'm getting a V1 here of 0.4243 meters cubed per kilogram. Again, you see this is just an intermediate step. If you can't do this, you can't get to a solution. That means you will most likely fail this problem. Make sure you can do this step on your own. This is 2 exams ago. Okay? You've got to get good at this stuff. Practice, practice, practice this stuff. You can't do it right now. Okay? Okay, saturated vapor, and we go find this specific volume value and try to find the saturated vapor at this specific volume. You're not going to find this exactly. You're going to be between a couple of rows. So pause it and see if you can find it real quick. Okay? Pull it over here. Pause it and see if you can find it real quick. If I'm on the pressure table, so assuming you're going again now, on the pressure table, oh, I'm looking at English now. Okay. It looks like that's going to occur between 400 and 450 kilopascals, right? Or between somewhere around 145 degrees C, not exactly. Yeah, somewhere between 145 and 150 degrees C. So you're going to have to interpolate this one. Now, I've already done this for us here. That is 6.8649 is what it looks like I've got here. That's kilojoules per kilogram Kelvin. You pause it and do the interpolation. If you can't do the interpolation quickly, you need to practice that. So pause it and finish the interpolation here. Okay, U2 is going to be 2556.3 kilojoules per kilogram. Seriously, you got to be fast at this. Okay, we got everything now, right? We got U's, I got S's. That's all I needed here and here. Now it's just run it through a calculator. Okay. All right, so let's see if I've got. It's a little more than my tablet can handle. This little tablet just doesn't. Let's see if I can pull it up. The slide that's got all the properties on it, I know really locks that tablet up. There we go. So I've at least got answers here. Maybe it'll load it. I don't know. It might not load though. I can pull it up. I've got it on my laptop here. Yeah, I don't think it's going to display it. Okay. The work, being the mass, 2 kilograms times our U values. All right, so I've got those here. Let's just move this out of our way. This isn't helping us anymore. So I do have answers pulled up on my computer over here. It's just barely off your screen. That's 2 kilograms times U2, 2556.3 minus U1, 939.45. Both of those are kilojoules per kilogram. So I'm getting the electrical work required to achieve this, to boil all this water off, so to speak. 33.7 kilojoules is what I'm getting there. Make sure you run that through your calculator and check that. The amount of entropy generated, which is equal to delta big S, right? That's M times, well, it's M times little s2 minus little s1. That's 2 kilograms times little s2, we said is 6.8649. 6.8649. By the way, I'm factoring my units out. I'm going to write them one time outside the parentheses. S1 is 2.88168. Those are both kilojoules per kilogram Kelvin, so I'm going to factor that out. So the amount of entropy generated, I'm showing here to be about 8.1 kilojoules per Kelvin. And I don't know how useful that quantity is other than just tell us because it's positive tells us what? Positive tells us because it's quantity, it's generating entropy, that tells us something. It's possible. It's irreversible. And that's a great stopping place. You guys have a good night. Lab Pop.